is a plane in 3D, and it's not passing through 0, 0, 0, because if you plug in 0, 0, 0, it doesn't, the equal sign doesn't work. So if it's x, y, and then z, the x-intercept is 10, y-intercept is 5. So you get the y-intercept by plugging in 0 here and 0 there, right? So it's 10 here, 5 here, and 5 there. There are these three points, 10, 5, 5. You connect that as a plane. Okay, so you connect these things to give you a triangle. And there's a unique plane that's passing through that triangle, okay? So you have that plane in 3D. Okay? Now the question is, of all the points that's on this plane, which point is closest to the origin? There should be just one, right? Okay, so let's try to solve this. How do you solve that? Well, what is the closest means we have to minimize the distance. So closest means minimize distance from x, y, z. Let's say x, y, z is the point on this plane, okay, to 0, 0, 0. Okay? And we know that the distance function is x minus 0 squared plus y minus 0 squared plus z minus 0 squared. So it's going to be square root of x squared plus y squared. So we're trying to minimize this function where x, y, z satisfies this. Is that good? All right. So tell me what the objective function here is. Yeah?
The distance function?
The distance function. This, because you're trying to minimize this. This is the target for minimizing. Okay, so you have fxyz as square root of x squared plus y squared plus z squared. Then what's the constraint? You see an equation, that must be the constraint, right? Yeah. What's the constraint? Gxyz is?
X plus 2y plus 2z equals 10.
No,
You
you don't put that equals to 10. If you're given an equation, move all the variables to one side so that that function is equal to constant, and that left side is the constraint, okay? So that's what we have. Now, we could just start the Lagrange multiplier this way, but we are going to modify this one so that fxyz is x squared plus y squared plus z squared. That's because for this to be as small as possible, the thing inside the square root has to be as small as possible, right? Yeah. Now, why would I want to do that? That's because differentiating a square root sucks. I don't want to do that, right? So if you can avoid having to differentiate the square root, by all means, try it. Okay, so just make an argument that if you have square root of something and you're trying to minimize it, the thing inside the square root must be minimized. Yeah, so you change that. Okay. Now, if you are not sure what I'm saying, then try this out. After I solve this, go home and try to differentiate this instead. Okay, try to find the gradient of this instead. Okay, and do all the calculation. It'll be longer and harder, but at the end of the day, your answer should agree with what I do. Okay, so that's like one way to simplify your calculation by a lot. Now let's put everything into the Lagrange multiplier. We need the gradient of f. The gradient of f is simply 2x, 2y, 2z. Okay. And the gradient of g, what's gradient of g? Gradient of G is,
1, 2, and 2.
yeah, 1, 2, and 2. Therefore, the Lagrange multiplier, which is gradient of f equals lambda times gradient of G, can be written here, and you say gradient of f, no, this one, 2x, 2y, 2z, it must equals to lambda times 1 times 2 times 2, 1 comma 2 comma 2. So here's the difference between people who only know Lagrange multiplier just as a formula and those who have the geometric intuition behind it. See, those who know what this equation means knows that lambda is just there to say that two vectors are pointing at the same direction. That's all it is, okay? So they have the freedom to say, well, we're just calling that as lambda. Why don't you call it as 2 lambda? That's still okay, right? Yeah. Why would I want to do that? Well, that's because everything here has 2 in there. So when you solve for x, y, z, it's easier to solve if you have a 2 there, because then you can cancel the 2 out. Neat, right? It's like calling 3 as 2 times 3 over 2, something like this. Okay? So if lambda was 3, now we call that lambda as 3 over 2, but there's a 2 times lambda. It's like different ways of calling the same number. So that's a way to save some time. And therefore, if I divide by 2, I have x equals to lambda, y equals to 2 lambda, and z equals to 2 lambda. If I didn't have that 2, I'll end up with x equals lambda over 2, y equals to lambda, z equals lambda. It sucks. Yeah. It's not as great. Okay, so that's nice. Oh, but wait, we still have 4 unknowns, x, y, z, lambda, 4 unknowns, and we only have 3 equations, right? 1, 2, 3 equations, right? So we can't solve it fully. So what do?
Plug lambda into a constraint.
See, your constraint is the 4th equation, right? So once you solve it, now you plug everything into the constraint, which becomes lambda plus 2 times 2 lambda plus 2 times 2 lambda equals to 10. Okay. And then that's 1 plus 4 plus 4, which is 9. Lambda equals to 10. So that lambda is equal to 10 over 9. Lambda equals 10 over 9. All right. So you have 10 over 9. Now what? Oh, that's it. Yeah, so now you have x equals to 10 over 9. Y equals to twice of that, so 20 over 9. Z equals to 20 over 9. So the answer is the point that's on this plane that's closest to the origin is 10 over 9, 20 over 9, 20 over 9. Okay. Try finding this using other calculus methods. It's impossible.